Okay, so we're going over 2003 AMC 8 problems. Okay, let's get started. Like always, I will give you guys some time, around 8 to 10 minutes, to complete a set of four problems, and then after that, we'll talk about it. So you guys can get started. Make sure you have like a pen or paper every time you come, and I'll tell you guys when time is almost over. So about 3 or 4 more minutes. All right. That is around 10 minutes. So what I'm going to do is go on and start on problem one. So I've gotten a couple of answers. Okay, should be working now. I'm going to reshare that screen. All right. So problem one tells us to do. Actually, can you guys hear me? Can you type in chat if you can hear me? Not sure. All right, cool. Cool. So problem one says Jamie counted the number of edges on a cube. Jimmy counted the numbers of corners, and Judy counted the numbers of faces. Then they added the three numbers. What was the resulting sum? So first one is pretty simple. We're basically going off knowledge that we already know, right? So let's just draw out a cube, right? I have my basic cube. Here, I'll draw out the insides just to be clear. So on a cube, we know the amount of corners is what? 8, right? We have 1, 2, 3, 4, 5, 6, 7, and 8. So that's 8. We're adding up the edges now. That's 1, 2, 3, 4, 5, 6, 7, 8 as well. Or sorry, 12 edges. And then for the amount of faces, there's 6 faces. So after we add that up, we get 26. So that one was pretty simple. There's certain things that you can memorize. For example, what a cube looks like, the amount of faces, the amount of edges, but it's not necessary. If you ever find yourself in need of like a diagram, you can always just draw one because a cube is pretty simple, right? So let's move on. For number 2, it asks, which of the following numbers has the smallest prime factor? Okay, so this one's a little bit more complicated. There's actually 2 ways of completing it that I can see. And number 1 is the more complicated way. So usually on a lot of problems, you'll have a complicated way to do a problem and also a simple way. See, the complicated way would be to take the prime factorization of every number. So as a reminder, the prime factorization is just dividing a number by all the numbers that, well, it can be divided by, right? So for example, for 55, we can do 5 and 11. What, can we divide 5 by anything else anymore? Well, no, we can do 1 and 5, but that's a little redundant, right? Because we're not learning anything from 1 and 5. So we can also do that for 57. So for 57, it'd be what, 3 and 19, and then we can check 3 and 19. And well, they can't be factored anymore. And we can keep doing that for 58 and 59, 61. But that would take a while. Not too long, but it would take a while. So instead of doing that, it's asking for the smallest prime factor. And we can think a little bit, what is the smallest prime factor? Well, we know it's not 1 because 1 is redundant, right? 1 doesn't help us with anything. If, for example, I try to factor 5 and I put 1 and 5, that's still 5. So 1 is not a prime factor, but 2 is. 2, therefore, is the smallest prime factor possible on the number line. And then now we can look at which of these numbers has 2 as a prime factor. So we know odd numbers can't be divided by 2, so it's not this one. It's not this one. 58 can be divided by 2. It's not this one, and it's not this one. So it seems like C, 58, is the only number that can have 2 as a prime factor. And since 2 is the smallest prime factor, we can say that the answer is C without having to check the other ones. So this right here was an example of using a quicker technique instead of having to check all of the problems. So, number 3, a burger at Ricky C's weighs 120 grams, of which 30 grams are filler. What percent of the burger is not filler? So keyword not filler. Okay, so we know 30 grams is filler, and we know we're trying to find what is not. So let's do this. The whole thing, so 120 grams minus 30 grams is 90 grams. And what does 90 grams represent? Well, it represents what is filler, right? But we can't just say that's the answer. Some people might just put E right here, but they would be wrong because it's asking for the percent, right? So we have to find the percent, and that's not too hard. We just set this up as a fraction. 90 divided by 120, that's 3/4, which is 75%. Or if you went through the steps, you would get 0.75. That converts to 75%. So the answer here is D. Okay. And as always, if you guys have any questions, feel free to type in the chat. I will answer as best as I can. Okay. So number 4, a group of children riding on bicycles and tricycles rode past Billy Bob's house. Billy Bob counted 7 children and 19 wheels. How many tricycles were there? All right, let's identify what we know and what we want to know. So we know there are 7 children and 19 wheels, and we're trying to see how many tricycles. So we know that a bicycle is 2 wheels, and a tricycle is 3 wheels, right? And we're trying to find how many tricycles there are if there are 7 children and 19 wheels. So again, there's 2 ways to do this. I'll go over both of them actually. The first way I would do is actually see how many wheels there would be if all the children rode on bicycles. So let's pretend that all 7 children rode on bicycles. So that's 2 times 7. That would be 14 wheels in total. Now, how many are we missing? We're missing, what, 19 minus 14 equals 5 wheels. Now, those 5 wheels are going to go to tricycles, right? So instead of having 7 kids on a bicycle, we need 5 more people on a tricycle. So I would say there's 5 people that are actually on a tricycle and the other 2 on a bicycle. So let's add this up. 2 times 2 is 4. 3 times 5 is 15. If we add that up, we get 19, which is the amount of wheels that we see. So that is a more intuitive way to do it. There's also an algebraic way, if you would like. If your algebra is a little bit more advanced, you might see this immediately. So let's represent the amount of children riding on bicycles as B and the amount of children riding on tricycles as T. So we know B plus T equals 7 because there's 7 children. And we also know that the amount of wheels is just 2 times B plus 3 times T, and that equals 19. 2B, so depending on how many bicycles there are, we have to multiply by 2. Depending on how many tricycles there are, we have to multiply the wheels by 3. So we now have a system of equations. So if you know how to solve a system of equations, that's great. If not, we actually have a video on our YouTube channel and on our website on how to do this. But it's not necessary for this problem, but it's great to have. There's a couple ways to do this. I'm just going to do the way that I like the most. So I just multiply it so that we can cancel out this 2b here. So I'm going to subtract this top one from the bottom one, and then I will get c equals 5. So the amount of tricycles is 5. And then we can plug 5 back in into here. So if b plus 5 equals 7, then b must equal 2. And there we go. Technically, we didn't even need the b, right? We already found the answer. It's E, 7 tricycles. Okay. Are there any questions on the past 4 problems? I know I went a bit quick because we were having some audio issues earlier, but any questions? Okay, seems good for now. Let's move on. So there's actually only 3 problems on this page because, well, you'll see the next 3 problems are actually connected. So I didn't want to split it up. But you guys can work on the 3 problems. You'll have slightly less time than before because it's only 3. But you can start. Let's do 2 more minutes. All right, let's go over the problems. So, first problem, number 5. If 20% of a number is 12, what is 30% of the same number? Okay. So what do we know? Well, we know that we currently have 20%, and we know that a number, and we know the result of the equation. So a number, let's represent by n, right? Perfect representation for a number, n. If 20% of this number is equal to 12, so 20% times n is equal to 12, what is 30% of that same number? All right. How do we do this? Well, we just multiply it out, right? 20% is 0.2 times n. That's 12. Instead, if you don't want to do 0.2, you can do 1 over 5 times n equals 12. And then we can multiply both sides by 5. That gets us n equals 60, right? And then now, since we know what n is, we're trying to find 30% of the same number. So now we do 30% or 0.3 times 60 equals 3 over 10 times 60, which equals 18, right? This can cancel out to 6. 3 times 6 is 18. So that's our answer, 18. This one's pretty self-explanatory. You just have to recognize that we're trying to find an unknown number, and we already have this information, and we have this information. So usually they just skip straight to this, right? But this time we have an extra step. We have to find the number in the first place. So number 6 says, given the areas of the 3 squares in the figure, what is the area of the interior triangle? Okay, let's find the interior triangle first. This right here, right? That's what we're looking for. What do we need to find the area of a triangle? Well, we actually have a formula for this, right? Area of a triangle is 1/2 times base times height. That's the area of a triangle. And do we have the base and height here? Well, at first it doesn't seem like it, but we are given these squares that do. So for example, they do have their edge on the triangle. So let's just look at the 144 square. Whatever this edge of the square is also the edge of the triangle. Or in this case, that would be the base. So base of the triangle. So how do we find one of the edges of this square? Well, we know that on a square, the side times the side equals the area. And we have the area, right? We have side times side equals 144. So essentially what we're doing is we're doing s squared equals 144. So in order to find s, we take the square root of 144, and that gives us 12. So the side of this square is actually 12. And so therefore the base is 12. 1/2 times 12. Now we still need the height, all right? How do we find the height? Well, luckily, we're given another square right here. And this has an area of 25. And we can use the same process. We know that s squared equals 25. And so s is the square root of 25, which is 5. So the side length, all of these sides are 5, including the height. So we write that down. 6 times 5 equals 30. Does that make sense? As always, if there's any questions, make sure ask in the chat. I will respond. Okay. Moving on. Problem 7. Blake and Jenny each took 4 100-point tests. Blake averaged 78 on the 4 tests. Jenny scored 10 points higher on Blake on the first test, 10 points lower than him on the second test, and 20 points higher on both the third and the fourth test. What is the difference between Jenny's average and Blake's average on these 4 tests? Okay, well, we already know Blake's average. That is 78. We're trying to find what Jenny's average is. How do we do that? Well, we know that Blake averaged 78 on each of the 4 tests, right? So on each of his 4 tests, he has an average of 78. So what was his score in total? How many points did he have in total? Well, we do 78 plus 78 plus 78 plus 78. So basically 78 times 4, and that gives us 312. And you can do the arithmetic on yourself. Right now, I'm just writing it down so it's quicker. Now, if this is the total amount of points that he has, then how do we find the total amount that Jenny has? Well, Jenny scores 10 points higher than Blake on his first test. So that's 10 more. Scores 10 lower than him on his second test. So that's 10 less. Scores 20 points higher on both the third and fourth tests. So that's plus 20, plus 20. And if we add those all together, we get plus 40. Jenny has 40 more points than Blake on her test. So we can add that to 312. Right? And then we're trying to find the average of Jenny's tests. So we're just going to divide by 4 tests because she also took 4 tests. And the average is everything combined divided by the amount of tests. So if we solve this, we get that she scores an average of 88. Now, all we have to do is subtract this by 78 because that is the difference between them. And then we get 10. So the answer is A, 10. Okay, this one was actually a little bit hard. I think the hardest part about this for me was recognizing that I can find the total amount of points that Blake has just by multiplying 78 by 4. Because on each of his tests, he has an average of 78. So maybe it's not exactly 78. Maybe on one of his tests, he got 77. Maybe on one of them, he got 79, right? But the average is 78. So we're allowed to just multiply 78 by 4 to find the total amount of points that he got. All right. All right. So this one's a bit strange. These are actually connected. I haven't seen this much in the AMC 8, but problem 8, 9, and 10 are actually related. So refer back to problem 8 when you're working on 9 and 10 as well. I will give you guys around 7 to 8 minutes for this one. Good luck. One more minute. All right, guys, let's start going over the problems. I know we didn't get a lot of time for this one, so it's okay if you didn't finish all of them. It was actually pretty difficult and relies on one concept, I think. And that concept is the area of a trapezoid. And I'll talk about that later. But let's read the problem first. Okay, so four friends, Art, Roger, Paul, and Trisha, bake cookies, and all cookies have the same thickness. The shapes of the cookie differed as shown. So Art's cookies are trapezoid, Roger's cookies are rectangles, Paul's cookies are parallelograms, and Trisha cookies are triangles. If each friend uses the same amount of dough and Art makes exactly 12 cookies, who gets the fewest cookies from one batch of cookie dough? Right, that's a lot of information, right? We're trying to find how many or who gets the fewest cookies from one batch. So everyone's batch has the same amount of dough. Okay. Right. It says right here they use the same amount. And we know how much Art makes. So if we can find out how many Art makes, or we know how many he makes, if we can find out how much dough it takes him to make a single cookie, then we can find out how much dough it took to make the entire batch, right? And that would be the amount of dough here. Oh, sorry, the amount of dough. So let's start doing that. If Art makes 12 cookies, we multiply 12 by the amount or by the area of each cookie or the amount of dough that each cookie requires. So here is where we get to the area of a trapezoid. So this is something, if anything, I'd want you guys to take away from this lesson, in that the area of a trapezoid is the average of the bases. So the average is just one base plus one base divided by two, because there's two bases, times the height. So it's very similar to a rectangle. Rectangle is base times height, but here we have two different bases, right? So we need to take the in-between, right in the middle of those two bases, and that's the average. So the area of his trapezoid in this case is 3 plus 5, that's 8, divided by 2, that's 4, times 3 is 12. So it takes 12, let's be more specific, 12 inches squared of dough to make one single cookie. And how many cookies does he make? Well, he makes 12 cookies, right? So 12 cookies times 12 inches squared is 144 inches squared. And that's how much dough they get for one batch. Everyone gets 144 inches. Everyone. So this is actually going to be helpful in our next questions. So let's save this numbers in our head, all right? 144. But for this question, it's actually just asking who gets the fewest cookies from one batch. So what I'm going to do is I'm actually going to find the area for all of these. For this rectangle, this one's much easier, right? Area is just base times height. That's just 2 times 4, which is 8 inches squared. For this one, since it's a parallelogram, we can still do base times height. So 3 times 2, 6 inches squared. And then for this triangle, the area is 1/2, 3 times 4, 1/2 base times height, which gives us 6 as well. So what can we gather from this information? Well, we know that if a cookie takes a smaller amount of dough to make, then they can make more cookies, right? If my cookie only takes 1 inch squared, then I can make a whole 144 cookies. So the smaller the cookie, the more they can make, which makes a lot of sense because they only have a certain amount of dough that they're allowed to use. So whoever has the biggest cookie is obviously going to have the fewest cookies because they need to use a lot of dough to make one single one. So who has the most or the biggest cookies? Well, that's obviously Art. He has 12 inches. The other ones have 8 and 6. So the answer for this question is Art. Okay. So let's save this number, 144, very important. And we're going to move on to the next question. And I'm just going to write that down after I delete all this. 144 inches squared. We figured that out, and this is amount of dough per batch for everyone. And we need this because for this question, it asks each friend uses the same amount of dough, right? Same amount of dough. We've already found it. And Art makes exactly 12 cookies. Art's cookies sell for 60 cents each. And to earn the same amount from a single batch, we're trying to find how much one single one of Roger's cookies should cost for it to cost the same as Art's. So how do we approach this question? Well, I would do this by we know that the area of Art's cookie is 12 1 inch, and we use that to find that 144 inches is the amount that they all get to use. So that means Roger also has 144 inches squared. Since Roger's cookies, as we found from the other one, here, let me draw out his cookie. It's 4 inches by 2 inches. His cookie is 8 inches squared. That's how big it is. So how many cookies can you make? Well, you can make 144 divided by 8, right? And that's 18 cookies. So in total, the amount of money Art will earn is, the amount of money Art will earn is 12 times 60, which is 720, because Art makes 12 cookies and they sell for 60 cents each. So he makes 720 cents. Now, Roger also needs to make 720 cents. However, he can make 18 cookies. So how much does he need per cookie? Well, that's 40. All right, 720 divided by 18. So he only needs 40 cents per cookie. So that's the answer right there. Okay, so this one was, a multi-step problem, right? We had to look at a lot of things. We also had to use information that we got from the previous problem. But once you dumb it down, right, you identify everything that you need to know. Like, for example, we found Arts, we found Rogers, and then we found the amount of money that Art makes, and therefore the amount of money that Roger needs to make. Okay. This next question is again a continuation, and it asks how many cookies will be in one batch of Trishna's cookies. Okay, this one actually is a little bit easier than the previous one. Here's what Trishna's cookie looks like. It's 3 inches by 4 inches, and it's a triangle. It's a right triangle, all right? So, again, this is how much dough she gets to use, 144. The area of her thing is 1/2 times 3 times 4. That is 6 inches squared. So all we have to do is just divide 144 by 6, right? The total amount she has by the amount she needs to make a single one. And that gives her 24 cookies. So a lot simpler than the previous one. All right, so that is it for those three. Okay, so we don't have a ton of time left. What I'm going to have you guys do is try these. Mainly focus on problem 12 and 13. If you do have time before I stop you, you can move on to problem 14, but it's okay if you don't. You only get about 4 minutes here. You can get started. All right, I'm going to start explaining the problems. So, problem number 12. It asks, when a fair six-sided die is tossed onto a tabletop, so a dice, right? You have six sides, 1 through 6. The bottom face cannot be seen, right? Obviously, when you throw a die onto the table, the bottom face is on the table. You can't see it. You can see the other five though, right? The one on the top and the four sides. And it asks, what is the probability that the product of the numbers on the five faces can be seen is divisible by 6? Okay. What is the probability that the product of the numbers on the five faces that can be seen is divisible by 6? What are the possibilities? So we only really have 6 possibilities, right? The first possibility is, for example, our 1 is covered, right? If our 1 is covered, then what we can see is our 2, 3, 4, 5, and 6, right? But for example, if I have a dice, back to drawing cubes, maybe I have a 1 here, I have a 2 here, I got a 3 here, maybe I have a 4 on that side, and a 5 on the back side, and a 6 on that backside, right? And my 1 is on the floor, and it's covered, and I can't see it. So it's asking for the products of the numbers that I can see. The product of the numbers that I can see is 2, 3, 4, 5, and 6. Okay. And it's asking, what is the probability that this is divisible by 6? Okay, so let's just list out all the other probabilities. If 2 is on the floor, so if 2 is touching the ground and we can't see 2, then the numbers that we can see are 1, 3, 4, 5, and 6. If 3 is on the floor, then what we can see is the other ones other than 3, right? There's no 3 here. And so on. This is if 4 is covered. This is if 5 is covered. And this right here is if 6 is covered. Now, when you're actually solving the problem, you don't really have to write these out, and you'll see why. There's actually a pattern to this. I mean, first of all, it's asking if it's divisible by 6. Which one of these are divisible by 6? Well, this one literally has a 6, and so does this one, and this one, and this one, and this one, which means they have to be divisible by 6, right? So this one's good, and this one's good. Now, is this one divisible by 6? Even though it doesn't have a 6, it does have 2 times 3, and 2 times 3 is, in fact, 6, which means this number is also divisible by 6. So if every single one of them is divisible by 6, then the probability is 6 out of 6, right? 6 of them give you this option out of 6 possibilities, which is just 1, which is E. Okay. Number 13. 14 white cubes are put together to form this figure. The complete surface of the figure, including the bottom, is painted red. The figure is then separated into individual cubes. How many of these individual cubes have exactly 4 red faces? Okay, so we've painted everything red. So all of this is red. But what isn't red is, for example, the faces that are touching each other. So you see this edge, this face that's in here, that's not red because, well, it can't be painted, right? This cube right here is touching this bottom cube. So the face is not exposed. So what cubes have 4 faces that are exposed to the paint? Well, let's look at these cubes on the top. This one has 1, 2, 3. This one right here and this one right here has 5. So these top cubes won't work. What about these bottom corner cubes? Well, these only have 1, 2, 3, right? Because on this side, they're covered by the top. On this side, they're covered by the left. On this side, they're covered by the right. So these edge pieces don't work either. Okay, now the only option we have left are these center pieces, right? Let's count up how many these have. These have 1, 2, there's 1 on the back and 1 on the bottom. They actually have 4. So does this one, right? And so does this one. It's only touching 2 cubes. And since it has 6 faces, if it's touching 2 cubes, then 4 faces are still exposed. So let's count up how many edge pieces there are. There's 1, 2, 3, 4, 1 hiding back here, and the 6th one here. So the answer, oh, sorry, circled the wrong one. Not 8. Definitely not 8. The answer is 6. Okay. Last question. Okay. This one you guys might not have gotten to. I know I told you guys you don't have to do this one, but we're just gonna go over it really quick. I actually like this one. It's pretty fun. It's like a puzzle, right? So it's asking, we have this weird addition problem with all these variables. If t equals 7 and the letter O represents an even number, what is the only possible value for W? All right, so let's write out t first. T is 7. That makes this, whatever is down here, a 4, because 7 plus 7 is 14. And we carry it over, and that means F is also 1, but we don't really need to know that. So since this is 4, and this is where O is, we know that these two O's are 4, right? And so because of that, that gives us, this is 8. Now we need W to be a number that makes it, well, for example, okay. We need W to be a number less than 5. Why? Because if it was greater than 5 or 5, what would happen? Well, 5 plus 5 is 10, right? I would have to carry over this 1, which means this thing would no longer be 4. And that's not okay because O cannot be 5. It has to be an even number. So that means W has to be less than 5. W plus W has to be less than 10. So what are our options? Our options are 4, 3, 2, and 1. So looks like 1 is taken. Looks like 4 is taken. And so our options are 3 and 2. So do you guys know why it would be 3 or 2? There's a... Okay. This one's actually pretty tricky because we have to go a step further. If W equals 2, then our equation would be 2 plus 2 is 4, which means U would have to equal 4. And that's not possible because every letter stands for a different digit. We already know O equals 4. So that means U cannot equal 4, which means W cannot equal 2. So our last option is W equals 3. So this one you have to give a little bit more thought into, but it's not that much math related, right? It's like more of a puzzle, more of logical thinking. So, I mean, pretty fun. I think it's a great end to our class here because we are out of time. We actually went over a little bit. So thank you guys all for joining. Hope you guys learned something. And again, if you take away one thing from this lesson, it's the area of a trapezoid, all right? So let me just write it down for reference. Average of the bases times the height. That's the area. So remember that one. And you guys can leave. Thank you.